Okay? We're now going to talk about what it means to have the size of an input and what it means to be polynomial time in the input size. Let's say, for example, that capital N, when we read a number in this program here, and capital N is a large number, we'll let little n be the base 2 logarithm of capital N, which means that the size of the input is approximately little n, the number of bits in the input. All right, now let's run this program. You add up all the numbers from 1 to capital N and print that out. Now, how long does that program take? Well, it takes big N time, but big N is theta of 2 to the n. So the time complexity is exponential in terms of the input size, not polynomial. So you would say, well, isn't this O of n? Well, yes, O of capital N, but capital N has exponential size in terms of little n. On the other hand, the space complexity of the program is theta of little n. So this is an example of a program that is p space, but is not polynomial. Now we're going to talk about a polynomial time reduction of the independent set problem to the subset sum problem. Now this is the one reduction in the chain I gave you last week that I didn't do or haven't done yet. Now it's important to understand that when we're talking about polynomial time, we're not talking about polynomial in the size of the numbers in the inputs. We're talking about polynomial in the number of bits of the inputs. And in my last slide, I showed you how that could be very different. So let's take an instance of the independent set problem. An instance would then be a graph together with a number. And the question is whether there's an independent set of size 2. Well, I can see more than one of these, at least 3 choices of independent sets of size 2, maybe more. But let's take an example. Here is an example of an independent set of size 2 consisting of the vertices v1 and v2. Now, we don't need to know that answer in order to come up with these numbers. This is the numbers in the reduction. I'm going to take this instance, forget the green things for now, that's a solution, and take this instance here and reduce it to a sequence of numbers together with a total. Now, we're going to write these numbers in base 10, and because we're used to that, but we could actually use any base as long as that base is larger than the number of vertices in the number of edges in the graph. In this case, the graph has 6 edges, so we could use any base as long as it's at least 7. I'll use base 10. And all these numbers, these numerals are in base 10. And each xi corresponds to an edge, the edge labeled ei in the picture. And each of these is a power of 10. 10 to the 0, 10 to the 1, up to 10 to the 5. Now, the way the y's are defined, the y's are also numbers in the sequence. So in fact, we're going to have a sequence of length 11 because we have 6 numbers here and 5 numbers here. So of that set of 11 numbers, we want a selection of those totals equal to S, a given sum. And that sum will be written as 2, 1, 1, 1, 1, 1, 1. Now the 2 is K, and the other digits are all 1s. All right, now, the question is, how do you develop these numbers? You get those by looking at the graph. Y0 corresponds to V0. And each of the y's has a 1 in the millions place, the 10 to the 6th place. And for the other places, it's either a 1 or a 0, and that depends on which edges touch V0. So V0 touches E0 and E1, and so Y0, which corresponds to V0, has 1s in positions 0 and 1. The 1's place and the 10's place. Now the vertex V1 is incident on edges E0, E2, and E3, so Y1 has 1s in the positions for 10 to the 0, 10 squared, 100th place, and 10 cubed, which is the 1000th place. And similarly, let's say V2, that incidence that touches edges E1, E2, E4, so we have 1s in position 1, 2, and 4. Did I get that wrong? Yes, I think so. These are positions, I made a mistake there. Positions 1, 2, and 4 are here. There. Okay, because that's position 0. All right, now, likewise, V3 has incidence on edges 3, 4, and 5. So we have 1s in positions 3, 4, and 5, while the V4 touches edge 5, so it has a 1 in position 5. Now, there's always a 1 in position 6, which is the next number beyond 5. So that this in the millions place, when we want to sum of these, we want to get exactly 1, 1 in every position, except 2, which is the value of k, in the 6th place, the n plus 1 place. All right, now, let's see how that works. There are several choices here. I picked randomly V1 and V4, and so the choices for of the rocks or the items are Y1 and Y4. But that's not enough. We also need to have other edges. We need E1 and E4. Now I want you to look at the graph, and you notice that those are exactly the edges which are not incident on either of the vertices we picked. So I'm going to, let's see, 1 and 4, I'm going to pick x1 and x4. Now, let's see what happens when we add these numbers up. We're going to add this number, this number, this number, and this number. So let's see what happens. We have 1, 0, 0, 1, 1, 0, 1. Then we have 1, 1, 0, 0, 0, 0, 0. Then we have y1, which is 1, 0, and x4, which is 1, 0, 0, 0, 0. Now when I add those up, notice that there's a 1 in each place except for the 6th place, which has a 2. And so the total equals that. Now the question is that an if and only if condition? Well, yes, because in order to get that sum, every edge has to be covered exactly once, either being an incident to the vertex in question or separately chosen. Now how do you know that the set of vertices is independent? Well, if I had two vertices next to each other, they would each have a 1 in position, let's say these two, and this would have each of them would have a 1 in position 3, which would give you, in position 3, instead of a 1, you'd get a 2. And that would be not allowed. Anyway, why is this polynomial? It's polynomial because the input size is actually larger than just the values of the number. Sorry, smaller than the values of the number. So the input size is not 1,000,000 or something in the millions. The input size is not more than about 100 or about 50 or whatever it is, the number of bits that it would need to express all these numbers, not something in the millions. And so this transformation I gave you clearly takes polynomial time. In fact, I was able to do it very quickly. And so then from the fact that the independent set is NP complete, we can now conclude that the subset sum problem is NP complete. All right, now here's an example of a practical problem where we're making use of these two ways of looking at numbers. Suppose that n and m are fairly large integers, and we need to compute either the sum of the two numbers or the product of the two numbers. And of course, both numbers are inputted as strings of bits, and the outputs are also strings of bits. Now, we're going to reduce these to the number of bits. The input size is not n and m, it's the logarithm. So we'll say little n and little m are the logarithms of capital N and capital M. And then using the grade school method we learned in grade school, second grade, fourth grade, whatever, it takes O of n plus m time to add the two numbers and approximately O of n times m time to multiply the two numbers using the standard multiplication algorithm. Now, those are, of course, polynomial in the input size. Only one processor can do either of those two algorithms in that amount of time. However, it turns out that addition and multiplication can both be done with Nix class algorithms, meaning in polylog time with polynomially many processors. All right, now I'll give an example of one of these. To do the addition of n plus m, the time that we're required to do is log n plus log m. Now remember that little n is already log capital N, so this is really log of the actual input numbers. Now in terms of space, this comes out to be polynomial in the sum of the numbers of bits. So that fits the definition of the Nix class. I'll show you this algorithm somewhat later, but not in the next slide.